What I have here in front of me is a small control transformer. It's a step-down transformer. Notice you've got a big iron core on this, a large iron core. Iron wraps all the way around the transformer, wraps through the center of the transformer. So these copper windings are actually wound around a piece of iron. The iron itself makes the magnetic field created by the electrical much stronger. So the iron helps it in, well, producing a larger current. This transformer is very common. A large power transformer is no different other than in size and in weight. Now, what I'm going to do to this transformer here is I'm going to set it down and apply a voltage to the transformer. And what I'm going to apply to that transformer is going to be, supposed to be 100 volts. Let's take a reading. My variable transformer often changes a little bit. So we got 99.6 volts, 98 exactly, 100.1 volts. Now this transformer is going to step the voltage down. And by stepping the voltage down, it's going to reduce the voltage. So if I take a measurement on my 24 volt side, it steps it down to 21 volts. Now, how the transformer works, it's going to be on what's called a turns ratio. This is going to compare the amount of copper wire on the primary side of the windings compared to the amount of copper wire on the secondary side of the windings. The windings right there appear to be the same size wire. They're just amount of loops or turns. If I have 100 volts on the primary and 20 volts on the secondary, we have a ratio or a turns ratio of 5 to 1. I will have 5 turns of wire on the primary side for every 1 turn of wire on the secondary side. That steps the voltage down. And the ratio would work backwards, stepping the voltage up. We get more into that shortly. So transformers do not have to be complicated. They've been around for quite a while, and they're used throughout industries, throughout homes. They're used just about everywhere. Now let's go a little further, and I'm going to point you at a screen and let's look at transformers. Transformers, not as complex as they appear to be. The drawings on the screen right here show nothing more than 2 transformers. You have what's called an air core transformer, and you have what's called an iron core transformer. Drawings are similar. These two bars in between the transformer windings represent iron core. Now the difference in these transformers is the air core transformer is nothing more than 2 coils of wire with nothing in between them. Primary winding, secondary winding, and inside in the middle you got nothing. That's air. You see a lot of air core transformers in electronic circuits, see some in drives. They're not used too often in large power. The most common transformer you're going to use or see is going to be an iron core transformer. That's the most common there's ever going to be. Primary windings, secondary windings are wrapped around an iron core. So all the wires intermix with each other around the iron core. Now this is only showing one phase of that transformer. This is a single phase transformer. That's all that is. Now how the transformer is going to work is simple. On the primary side, as power goes in, that power passes through the coils. Okay, that power creates a magnetic field that induces a voltage on the secondary, and that voltage on the secondary flows in the opposite direction. Now, difference here is the air core transformer, if this has a secondary current of 0.5 amps. For an iron core transformer of the same size, the secondary current will be about 5 amps. So the iron core in between is going to help amplify the magnetic field and help right there increase the current ratings. So iron core transformers will be the most common. Now, as this sine wave right here rises and falls, you see the arrows rise and fall, that magnetic field expands and contracts. Well, as that power flows through the primary windings, it induces a voltage in the secondary windings in the opposite direction. So that transformer will invert the sine wave. It'll step the voltage up or step the voltage down. That's all based on turns ratios. Now, the second half of that sine wave, that magnetic field again is still passing through the transformer. We have to remember AC power flows one direction, it stops, reverses, flows in the opposite direction. So current flows one direction, current flows the other. The magnetic field fluctuates. It expands and contracts, expands and contracts. Goes in one direction, comes out the other direction. So it's either amplified the voltage or amplified the current. Now how the turns ratio works, it's pretty simple. If we have a turns ratio of 4 to 1, what that actually means is there are 4 coils of wire on the primary winding for every 1 coil of wire on the secondary winding. 4 to 1. So if I have a voltage going in on the primary of 100 or 480, my power coming out on the secondary is going to be 120. Now the same transformer with the same exact winding ratio, the same transformer, if it had a windings ratio of 2 to 1, and this is very common in industry, you get 240 volts going in and you get 120 volts going out. Well, my numbers are backwards on this screen, but how this works is I can also have a step-up transformer where I take 120 volts on the primary and I step it up and I get 480 volts on the secondary. So this transformer would be a 1 to 4 ratio. 1 to 4. We can do the same thing, 120, 240, 2 to 1 ratio. There's also a lot of transformers out there that have a 1 to 1 ratio. This is called an isolation transformer. You see a lot of these in control circuits. You see a lot of these controlling computers, drives, PLCs, a lot of different areas. What they're used for is a filter. It filters out a lot of the power quality issues that happen with electrical current. Electrical power is not exactly clean. It actually comes out pretty dirty, especially when it goes through a facility. So if I get 120 volts in, I'm going to have 120 volts out. So the turns ratio, this describes every transformer. So if I hook the transformer up backwards, it changes the ratio. Problem is, the numbers are embedded on the transformers. You create dangerous situations by hooking them up backwards. So they're only designed one way. Now, the most common type of transformer you see in industry is three-phase transformers. Three-phase. Here we have 1, 2, 3 single-phase transformers. Those single-phase transformers are joined together. Okay, so they form what's called a delta. So this is a three-phase delta transformer. That's common. Another method to create a three-phase transformer is called a Y. The same individual three phases, 1, 2, 3, are joined together at one point. This is now called a Y transformer. And these two transformers would be the most common you could ever come across. One side would be a primary winding, the other side would be the secondary windings. Primary versus secondary. Now, one of the transformers you got to watch out for is what's called a grounded delta system. These have been installed long time ago, older areas, older buildings, older equipment, you'll have what's called a wild leg or a high leg. The voltage on this transformer could be one of two voltages. You might have three-phase 480. So measuring between A and B, you get 480. Measuring between B and C, you get 480. And measure between A and C, you get 480. Problem is now, if you ground the transformer and connect it to ground, center tap it, this creates the neutral conductor. So if I have 480 between A and C phases, I measure the neutral and I get 240 volts from A phase to neutral, 240 volts from C phase to neutral. But if I ever measured B phase to neutral, this B phase right there is 208 volts. Well, 347 volts. It's 208 on the 240 volt transformer. If this is a 240 volt transformer, we measure 240 between any two phases. A to B, B to C, A to C, three-phase 240. Now if we ground it and create the neutral, we measure A phase to neutral, we get 120. We measure C phase to neutral, 120. We measure B phase to neutral gives you 208. So because of the higher voltage on either one of these, the code requirements or building codes require this circuit right there to be orange. There's not too many places inside of the code books that call for colors. Ground wires are green with yellow stripes are bare. Neutral wires are white or gray. And the high leg has got to be orange. Other than that, all the other colors could be used, well, at your discretions. So grounded delta, they're everywhere. Now, the most common circuit you're ever going to see is what's called a grounded Y. This is usually going to be the secondary side of the transformer, three phases. The center point of the transformer is grounded to earth. Okay, and from there, once it's grounded, this is where the neutral wire comes from. Now, in this circuit right here, you're going to measure between A phase and B phase, A and C, and you get 208 volts. You measure A to B, you get 208. Okay, you measure C to B, and you get 208. But now, if I measure anything like, say, A to neutral, I measure C to neutral, I measure B to neutral, it's going to be 120 volts for each one. So this is the most common transformer you're going to see. But also in industry, you're going to have the same Y-type transformer that puts out 480, 277. So in other words, I measure between A phase and C phase, I get 480. I measure between A and B, 480. I measure between B and C, 480. So three-phase 480. But now we get the neutral here. I measure B phase to neutral, it's 277. I measure A phase to neutral, 277. C phase to neutral, 277. Probably the most common you see in large industries. Now, also used in the U.S. and becoming more and more popular is 600 347. So 600 347 measuring between A and C, A and B, C and B, it's all going to be 600 volts. And if I measure the neutral, it's going to be 347. There's a lot of use for this type of transformer, especially when you start calculating the cost of copper wire. Now, another circuit you can see is going to be what's called an ungrounded delta. There's a lot of circuits that are grounded, such as this one and this one, and there's a lot of circuits that are not grounded. Now, in all reality, if you have three-phase equipment and all you run is three-phase equipment, you don't need a neutral conductor. So these systems are permitted to be ungrounded, but once they are ungrounded, there's a whole host of safety factors that got to be complied with. Now, In this circuit right here, for example, you measure between A phase and B phase, I might get 480. B to C, 480. A to C, 480. So this would be 480 volt three phase. Now on the other side of that coin, a lot of these transformers are only 240 volts. So I would measure 240 volts, 240, and 240. Point is, when you have an ungrounded system, all you're going to measure is one voltage. Only one. Now I could have an ungrounded Y system too. Now again, you're only going to have one voltage. That transformer will put out either 208 volts or it'll put out 480. Because there's nothing connected to the neutral point, there is no neutral wire. So I take my measurements between A and C, you get the 480. A and B, 480. C and B, 480. Okay, and if we're using a 208 volt three phase ungrounded, then all these measurements should be 208. So there are different types of transformer configurations. Now, one transformer you got to be aware of is this guy, and it'll get you right there. It's called a corner grounded delta. You see these in buildings that were built around World War I and World War II. So we're talking about older systems. Back in those eras, there was a shortage of copper, and all the copper went to make bullets. So any buildings built during that time used the building steel itself as a conductor. So this is where you take C phase and connect it directly to the building steel. And this energizes the building. So now you could measure from 480 volts to ground, from B phase to ground, and get 480. You can measure B phase to A phase and get 480. You measure A phase to ground and you get 480. So it's three phase 480, but one phase is grounded to the building. This system is perfectly safe to use, reduces the need for copper wire, but it's very tricky. It only has one building. On the downside, it can be very dangerous because if somebody working live gets between two phases, well, the likelihood of survival goes down. So this transformer can be hooked up as 240 or 480. And you'll see these in older areas, older buildings, things that are basically made around World War I or World War II. Now, the most common type of transformer system you're going to see is going to be what's called a delta Y system. This is the most common you'll see in industry. Okay, primary voltage can be anything. I have 480 as an example. Secondary voltage is typically going to be 208. All the primary windings are connected together in delta. All the secondary windings connected as Y. Now, the requirement here is the transformer case has got to be connected to earth. Well, this transformer is going to create magnetic fields, and as these magnetic fields expand, that's going to induce a voltage right there on that casing. So that transformer winding case has got to be connected to ground. So every case connected to ground, regardless if it's grounded or ungrounded systems. But standard voltages don't exist. Right here, the primary winding is 4,160 volts. In all reality, these windings could be upwards anywhere from 35 kilovolts and less. It's based on the availability at the utilities and the needs of the local facilities. The secondary voltage is typically going to be 480 or 208. It can be other voltages as needed. So we have different voltages. Now, here we have what's called a grounded system. These two systems are ungrounded. Okay, this system is grounded. Now, by taking the center part of that transformer and connecting it to the transformer case or the grounding electrode conductor, this now creates the neutral conductor. So I could have, let's say, 208 volts phase to phase. I could have 120 volts phase to ground or phase to neutral. And yet, right over here on the primary winding, there is no ground, there is no neutral. It's straight three-phase. I can have different transformer configurations. Here we have delta Y. We could also have what's called YY. Y primary windings, Y secondary windings. Now, these secondary windings do not have to be grounded on any of these transformers. So we could have ungrounded systems anywhere we need, but there are other safety requirements. But to avoid the safety requirements can be kind of intensive. It's a lot simpler to ground the system and use a neutral. Whether or not you use the neutrals up to the facilities. You got to look in the NEC code books for details and complete requirements. I could have transformers that are delta-delta. Once again, that ground right there that connects the transformers is optional. I could have delta Y, Y delta. I could have all kinds of configurations. So transformers themselves, every one of these windings are an individual winding. All three windings here are secondaries. All three windings up here are primaries. All connected together. The label of the transformer will actually have a picture of the transformer on the label. And it will identify what's delta and Y. It'll identify the configuration, with delta Y being the most common. Now, in most of the transformers on the labels, they're not going to show you A, B, and C phase. They're going to show you the letters H1, H2, and H3. The letter H will always represent primary windings. On the secondary drawings, again, they're not going to show you A, B, and C. You're going to see on that transformer X1, X2, and X3. X will always represent secondary. Off the center, there's typically a dotted line that reads XO. And this is the point where you connect the neutral wires. You ground the transformer and connect the neutrals. So transformer 101, guys. I could have delta delta, Y Y, delta delta, Y delta. We could have any configuration needed for transformers.